All right, well, I think we can go ahead and get kicked off here. So welcome to this week's installment of the Bureau of Economic Geology seminar series. We're very pleased to have Dr. Frank Tsai here with us today. Dr. Frank Tsai is a professor of water resources in the Department of Civil and Environmental Engineering at Louisiana State University and the director of the Louisiana Water Resources Research Institute. He received his PhD in civil engineering from the University of California, Los Angeles in 2002 and has been a faculty member at LSU since 2003. Dr. Tsai is a registered professional engineer and professional geoscientist in Louisiana. He is a fellow of the American Society of Civil Engineers. His research focuses on groundwater, hydrogeology, and water resources, with more than 2 decades of experience in subsurface data analytics and groundwater modeling. Dr. Tsai has published over 90 refereed journal articles and has mentored 14 PhD graduates. He currently supervises 6 PhD students working on groundwater research projects funded by state and federal agencies. So again, we're very excited to have you here with us, Dr. Tsai. As a quick reminder to everyone, please drop your questions or comments in the chat box and we'll address those at the end. So with that, I hand it over to you, Dr. Tsai.
All right. Good morning. Thanks, Justin, for introducing me. And I also want to thank Dr. Wang Yang Li for the invitation to give me an opportunity to present our research results in the last 5 years toward into the regional scale high resolution groundwater modeling. So this is a lot of work, and I thought I have 2 hours to talk, but I was advised finish within 40 to 45 minutes. So I apologize if I rush in my presentation toward to the end. All right, so the work basically funded by funding from the USGS, Water Resources Research Act, and the Mississippi Alluvial Plain Project, and the National Hydrological Geospatial Fabric. Okay, this is providing us the constant funding of source to work on this larger scale groundwater modeling. Also, we have being an ESCO state, and we have fortunate to have a National Science Foundation Track 2 5-year project. And also, this work is done through several relatively small short fundings in different agencies. And also, the disclaimers and the presentation will be basically the point of view of the presenter, which is me, and it's not the opinion or policy of the USGS. All right, so today I'm going to talk about groundwater modeling. So how do we build a complicated high resolution groundwater model? So I will start with the introduction of the Gulf Coast aquifer system with a focus on Louisiana, because Louisiana, Texas is all share the similar geological settings in the Gulf Coast plain. Then I will talk about we develop a very detailed data model framework for high resolution groundwater modeling. In order to deal with this very detailed geological model embedded in the groundwater model, we need to find a good model to run it, which is a MODFLOW. I will shortly discuss about the 6th generations of MODFLOW. And then we concentrate on how we build a statewide Louisiana groundwater model. And recently, we have the fortunate to work with USGS on airborne geophysical data, and we want to incorporate that data into our groundwater model, as well as the soil water intrusion studies. Finally, I'd like to talk about, hey, we have these pool tools and data, how we really work toward to the Gulf groundwater model for the entire Gulf Coast system. Now I give some closing remarks. So the first is the Gulf Coast aquifer system. So you can look into this aquifer system, which is very complex. If I use laser point over here, so this figure to the left is the U.S. principal aquifers. As you can see, the study area is really focused on the Gulf Coast aquifer system over here in the southeastern United States. And in this aquifer system, this is sedimentary rocks. It can be as deep as 4,000 feet below land surface, and is created by the glacial fluvial and the fluvial deltaic process, which create a very complex sedimentation or deposition of alluviums. Within this aquifer system, we have several major aquifer systems, which is MEAS called MEARS, which is on the upper part of the domain, which is called Mississippi Embayment Aquifer System. And near the coastal area across Texas, Louisiana, all the way to the Florida, this is the coastal lowlands aquifer system. And also we have MERVA, which is Mississippi River alluvial aquifer within along the Mississippi River. And then we have additional Texas coastal uplands aquifer system. And groundwater use basically occupy around 30% of water in this area, and another 70% of water come from surface water. So groundwater is really, really important in this system. So why we want to study groundwater in the Southeast US? Because groundwater depletion. As you can see, USGS published in 2013 about several major aquifer systems, including Central Valley of California, Central Valley Aquifer, and High Plain Aquifers, and Gulf Coast Aquifer system. They all represent the groundwater depletion, especially in the Gulf Coast Plain, that the groundwater depletion causes saltwater intrusion along the coastal line, and also land subsidence. So I think it's very important to really understand the aquifer system in order to deal with those groundwater issues. So the aquifers, what aquifer or aquifer system we have here? So within this aquifer system here is basically bounded by the this area is in the Central area, okay, including 10 states. And in my study area, I basically focus on the lower Mississippi Gulf region. I don't study Texas. Hopefully in the future, we'll study Texas. So looking into the chart over here, this system including the tertiary and the quaternary systems, and from the Holocene all the way down to the Pleistocene. In Louisiana, in the northern Louisiana part of here, basically the aquifer system is within the Mississippi Embayment aquifer system over here. However, in the southwest or southeast Louisiana over here is basically covered the coastal lowlands aquifer system. Later on, you will see we have around 15 different aquifers. Start from the Mississippi alluvial valley alluvium, the Chico aquifer, Evangelion aquifer, all the way down to the Claiborne, Wilcox, and Midway. So that's the complex systems we have, and we want to model it based on the data we have. So the focus is really the Louisiana principle of freshwater aquifers. So we have around 11 freshwater aquifer system within Louisiana, and also in Louisiana. Okay, you can see that along the coastal plains is blank. It's because of lots of solar water within the coastal areas. However, moving to the inland, we do have lots of fresh water we can use underground. In Louisiana, we want to build a model covered entire Louisiana and the southwest of Mississippi, and you can see the river system is very important for the recharge of those aquifer systems. And we have Red River, Ouachita River, and the Mississippi River. That will be the major river over here in the southwest of Louisiana. We have the Calcasieu River and Atchafalaya River. Also, we have Sabine River, which is a boundary between Texas and Louisiana. As you can see the figure to the right, Louisiana has actually cover two aquifer systems, which is Mississippi Embayment, and another one is coastal lowlands. Again, we have 11 freshwater aquifers. If you do this counterclockwise, from the Sparta Aquifer to the Carrizo Wilcox, which extend to the Texas, and the Catahoula, Jasper, Evangeline, Chico, Southern Hills, Red River, Mississippi Alluvial, and the Cockfield Aquifer system. So we have 11 freshwater aquifers. And we can get the freshwater aquifer down to as deep as 3,000 feet. And annually, Louisiana use around 1,600 million gallons per day groundwater for various purposes. Majority go to the irrigation, which cover 41%, and public supply 20%, industrial 15%, also aquaculture like crawfish, shellfish 19%. Sometimes we use groundwater for energy exploration like hydrofracking and exportation. And also the groundwater, fresh groundwater is very important to the Louisiana coastal wetlands. Well, we'll look into the Louisiana groundwater use in comparison to neighboring states. You can see from this picture, the highest groundwater we show is California, right? So we all know that they have groundwater issues in California. However, looking into the Southeast U.S., the major user state, groundwater user is Arkansas, which is north of Louisiana, and Texas. Louisiana relatively has a low use of groundwater compared to neighboring state. And again, groundwater use annually around 1,600 million gallons per day. So actually, Louisiana groundwater is really, we are competing with neighboring states and to use groundwater. So we have lots of groundwater issues in Louisiana, and which is common also in other states. We have overpumping, we have significant groundwater level decline that created a saltwater intrusion in different aquifer systems. Southern Hills Aquifer System, Mississippi Alluvial Aquifer, Chico Aquifer, Sparta Aquifer, they are all have lots of saltwater intrusion issues. You can see the figure to the right. Those are the data we collect from USGS. The maximum recorded chloride concentration parts per million. Like you can see, lots of area has a high chloride concentration in Louisiana. That also create land subsidence because of overpumping. We have land subsidence in Baton Rouge, New Orleans, and the southwest of Louisiana. And we also have transboundary groundwater issues, especially competing groundwater use with the South Arkansas over here through the Sparta Aquifer. So it's very important to know that a comprehensive statewide groundwater model for Louisiana is really essential in order to have effective address these groundwater challenges. So the second topic over here is that in order to create a high resolution groundwater model, we have a data model framework. This framework has been built over the last maybe 10 years, start from scratch and all the way down to the groundwater analysis or management. So we start from data collection. We collect the well logs and also recently the airborne electromagnetic data in order to understand geology first. To us, geology is very important. Without knowing the good geology, you cannot have a good groundwater model. So that's the principle. And then we start to collect groundwater use data from the 10 states within the Gulf Coast Plain. Then we look into the hydrogeological framework development. After that, we have a technique called horizon restoration based on some geological principles in order to build a lithological phases modeling. So the upper part of here basically is to build a good high resolution geological model. Once we have a geological model from the upper part, we go to a groundwater modeling area. We use MODFLOW, unstructured grid, and MODFLOW split, which is a model domain decomposition. And once we have that, we go into the MODFLOW 6 to develop packages for individual models. Then we have a techniques to for the large scale model calibration within the supercomputers. And finally, we will get the high fidelity groundwater models. Then we use this model for groundwater analysis and management. That's the workflow over here. Oh, sorry. And this workflow actually took lots of time and lots of PhD students and a master student to build. Okay, as you can see in the past 5-6 years, I have lots of a big stream of graduate students to make this possible. Some of them already graduated, some of them still working on this workflow. And through this workflow, we developed several data set techniques toward to the large scale groundwater modeling. So we have a data from well log and electromagnetic data. And we have groundwater usage data here. And here we have a we call this method horizon assisted lithological modeling. Here method I will introduce later to develop a geological model. And then go into the groundwater model. We have a unstructured grid maker called DISU maker. And we also have exchange maker to develop exchange packages to have a information exchange between submodels. Then we use the MODFLOW. Once we have several submodels, we do the parallel MODFLOW computation in the supercomputer. And also in the supercomputer, we have these techniques called parallel iterative ensemble smoother IES, which is very popular actually nowadays in USGS and also other area for large scale model calibration. And finally, once we do all the calibration, we have parallel MODFLOW 6, we can do groundwater analysis and management. Data, okay. Data is extremely important. We collect and digitize the geological logs and electrical logs over 9 states except Texas. Okay, as you can see the chart over here, from Alabama, Arkansas, all the way down to Missouri, Tennessee. We spend lots of time and manpower to digitize and analyze to make those well logs useful for aquifer depths, information for aquifer depths and aquifer thickness. We haven't worked on Texas data yet, although we already have on our hand. Hopefully, we will do that in the future. And given this huge amount of digitalized logs that we collect from the different state and federal agencies, we will be able to develop a good geological model for groundwater modeling purpose. The first method we consider is horizon-assisted lithological modeling. We call it HERM method. It's basically based on the law of stratigraphy. Again, I believe the audience is basically a geoscientist. They understand the law of origin, horizontality and superposition, cross-cutting relationships, and the lateral continuity. So we use those ideas to build this logical model. The first is do the domain transformation. We have several horizons. In these cross sections, we have horizons to create a unit 2, unit 1, unit 2, unit 3, and unit 4. And we have methods called a flexural restoration method to make it as a horizontal, to map into the horizontal domain. We call it non-dipping domain. We map the grid and the well logs into the non-dipping domain. Then we do interpolation. We can use the geostatistics. We can use other interpolation to create a geological model in the horizontal domain. Then we have transformation back to the deepening domain. That's what we create our lithological model in the real domain. So that's the Helm method. This is in cross-sectional view. In the three-dimensional view, using the Helm's method is more complex. That consider originally we have a horizons surfaces in the A from here, and we have a geological fault which is separated these two domains. So what we do is we go the north of the geology, go to the northern part, non-deepening domain, to create a lithological model in a non-deepening domain, then transform into a deepening domain. The south of the fault, this domain, is going to another route, also in a non-deepening domain, to create a lithological model. And later on, we put these two together into a one piece of geological model where you have a geological fault in between the two models. That's the approach we build a lithological model. All right, so regarding the groundwater or geological model for Louisiana, we obtained the horizons from the USGS. As you can see from here, those are horizons for Chico Aquifer, Evangelion Aquifer, all the way to the Wilcox aquifers. And those horizons help us to implement the Helm method. And we have lots of well logs in Louisiana we collected previously, and we interpret the electrical logs, especially for gamma ray, SP, and the resistivity, to understand where are sands and where are shale or clay. And once we have all those shale and sand intervals, we will use a geostatistics to build a lithological model for Louisiana. I will skip the details, tell you this is the results. So this is our Louisiana geological model. We on the top, we have soil groups from USDA, A, B, C, D. Below the soil layers, we have a clay and we have a sand. You look into the different cross sections, for example, the EE cross section in northern Louisiana, which belong to the Mississippi embayment aquifer system, you will see those blue areas are aquifers, different aquifers, and gray areas are clay. And there's a syncline toward to Mississippi River. If you look into GG prime, which is in the South Louisiana over here, from the Sabine River all the way to the Pearl River. As you can see, this is a very complex sedimentary hydrostratigraphy, okay, for Louisiana. And the blue represents aquifers. And you will see in the west, we have a Chico aquifer system. And the Chico aquifer actually connect to the Mississippi River alluvial aquifer all the way to the east, different aquifers. Looking into the north-south cross sections, you will see the two systems, the class and the meres. So in the northern part here, we have a Mississippi embayment aquifer system. And in the south part, we have a coastal lowlands aquifer system. Actually, in this area, we have two faults. We have Baton Rouge fault, and then we have Denland Spring Scotlandville fault. We call it DSS fault, which we can simulate. And you can see the discontinuity of the aquifer or aquitard across the fault. We have this very detailed geological model. The next question will be, hey, how we are going to model this now in terms of groundwater, right? If you look into a traditional ground or MODFLOW 2005, it's not going to help, right? So now MODFLOW 6 will be a very good tool to create a groundwater model like this. So I'd like to discuss briefly about the key advancement in the 6th generations of MODFLOW. We call it MODFLOW 6. Okay, so if you go to the MODFLOW website and you click the link, you will directly see all those information on the screen. So MODFLOW 6 initially released in 2017. The current MODFLOW current version is 6.6.1, released just a few days ago. Okay, I just visited yesterday to check it out. MODFLOW 6 is a sixth generation of MODFLOW. So before MODFLOW 6, you have a MODFLOW released in 1984, 1988, 1996, 2000, and 2005. If you are a groundwater modeler and use MODFLOW, you will understand this very well. And you will see a missing link here is now before MODFLOW 6 released, there's called MODFLOW USG. And MODFLOW USG was designed for the unstructured grid modeling. However, USGS did not classify MODFLOW USG as part of their core version. So the next core version is MODFLOW 6. The current MODFLOW 6 has a lot of features. It can simulate groundwater flow. It also can simulate soil transport, including soil water intrusion, and also can simulate groundwater energy, especially important for the geothermal studies, something like that, and the particle tracking. And I will skip this one, the MODFLOW basically built by Fortune, okay, but they have a Python libraries called FlowPy, which you can use to build MODFLOW 6 packages. MODFLOW 6 supports structured grid, unstructured grid, and the local grid refinement. You will see this later on in the next slides. And the MODFLOW 6 solve a groundwater model, which is groundwater flow equation, which is very simple using a control volume and finite difference method. The key feature over here is the gridding approach. So MODFLOW 6 allow two things. One is a domain decomposition, which you can split one big model domain into several models, and they can communicate through each other through exchange packages. Because of the domain decomposition capability in MODFLOW 6, MODFLOW 6 can do parallel computing. So once you can set up all the submodels, you bring into the supercomputer, or maybe you have a personal computer with multiple cores, you can do parallel computing easily. Okay. MODFLOW 6 can accommodate the various structured grids, like a quadrille Voronoi grid over here. And within the MODFLOW 6, there are three different discretization features. One is called DIS package, which is traditional. If you are traditional MODFLOW modeler, you can build the layers, rows, and columns DISU. So most of the people using this DISU feature. More advanced gridding is called a layered grid defined by vertices and in each layer. So this is called a DISV. I can see this picture to the right basically is the very important advancement of MODFLOW 6. You can do the layered structure, but within the layer, you can have this unstructured grid for DISV. However, MODFLOW 6 has a very important feature, which I think is the most important thing, is called DISU. It can have a very general structural grid-based concept, okay, which is really based on the MODFLOW USG. What is DISU? DISU, as you can see the figure over here, if you build a geological model, something like this, you don't really see a clear layer structures. Then you will be able to use DISU to model groundwater system based on this kind of geology. This is what we are developing at LSU. All right, so this gives you the ideas about the MODFLOW 6 gridding. Okay, this example in here, Baton Rouge capital area. Okay, we want to model groundwater over here in Baton Rouge area, and we have two geological faults here. What we do is that we can create a refinement in grid along the fault, of two faults, also along the area of interest that we want to see more details. And MODFLOW 6 can handle this kind of von Neumann cells grading approach. Also, once we build a geological model for the capital area, we separate our domain into 3 domains. The middle model 2, the model 1, model 2, and the model 3, and the model 2 will be the most important groundwater model to us. So we can have 3 submodels. They all talk to each other through the exchange files. In total, we have 2.6 million cells, 3D mail cells, but once we break into it, we can run the MODFLOW 6 much easier and faster through the parallel computing. So through the domain decomposition, this is a MODFLOW structure over here that it can build all kinds of packages, like recharge package, like a drain package. Okay, you have a groundwater pumping well package and so forth for individual models. And we have model 1, model 2, and model 3. What we need to do is to build a groundwater flow to groundwater flow exchange file to communicate between each pair of models. Once we can do that, we can run MODFLOW 6 easily, and it's very, very useful for unstructured grid, something like this. No, they can talk to each other through the unstructured grid. So once we understand the capability of MODFLOW 6, domain decomposition, parallelization, and also the unstructured grid, we can start to look back to our Louisiana groundwater model. So we build a Louisiana statewide groundwater model based on here. We have more than 21,000 pumping wells in the state. And for the boundary conditions, for the groundwater streams, lakes, oceans, we use NOAA's national water model. And then we also use ocean circulation model for the ocean boundary conditions. And for the northern and east and west boundaries, we use USGS groundwater data through several observation wells. And the recharge data, we use RAISE and Sanford's. They publish monthly recharge data in 2019. But in terms of groundwater modeling, we split this model of groundwater into the 9 regions, 9 sub-regions. You can see here, 1, 2, 3, up to 9, which is based on the Louisiana Watershed Initiative. So what we do is that we collect different data for groundwater modeling over here, but really looking into how we split the Louisiana groundwater model based on the HUC 8 and HUC 6 watershed boundaries. As you can see, if you look into detail here, that will be model 1, model 2, model 3, all the way to model 6. So first, we have a tool to create 9 DISU packages for unstructured grid. And then you can see those links. There are 16 links among 9 models. So we built a 16 groundwater flow exchange package such that they can communicate to each other in the MODFLOW 6 model. Then the next level is really go to the model calibration, which is the inverse problem. We use a pilot point method. We calibrate groundwater model for different parameters like hydraulic conductivity for aquifers, specific storage for aquifer aquitard, and also conductivity for soils, and for also other forcing terms over here. In total, we have 1,000, literally over 1,000 unknown parameters. That's what we want to adjust our model parameters. So this inverse problem, we have observation groundwater data, and we apply a optimization method. It's called a Levenberg-Margrat-based iterative ensemble smoother. To solve the high-dimensional inverse problem, we apply this ensemble smoother in the parallel computing, which we can run like 300 realizations at the same time, and to calibrate the groundwater model. This is we spend like millions of hours. Okay, although I did not show here, we spend lots of hours, computation hours in supercomputer for model calibration. And this is the results. So we have model calibration from 2004 to 2008. We have more than 5,000 observation data. We get a very good root mean square errors in groundwater level. 3.5 meters is not really not bad at all. And in the model validation data period, we start from 2009 to 2021, and the root mean square error increased just a little bit now, 30 centimeters, 0.3 centimeters. So I suddenly say my okay. All right, so then you can see this is our one result of our groundwater model output. This is simulated the groundwater head at the end of 2021, and it shows that several cone of depressions in Louisiana. We have a biggest cone of depression right here in Baton Rouge area. Then we have a cone of depression in the southwest of Louisiana because of agriculture, pumping, and because of petrochemical effect plants that need lots of groundwater. In the northern central area, we have spot aquifer depletion over here. And also in New Orleans, we also have apparent cone of depression is because of industrial pumping. Before we build a statewide groundwater, Louisiana groundwater model, before we do that, we actually, before that, we built a lot of different groundwater model at the different places in Louisiana. Now we can compare our Louisiana model with the previous model, which we built based on MODFLOW 2005 and MODFLOW USG. Starting from last year, we started to publish MODFLOW 6 results. So you can see the large cone depression occur in the capital area groundwater depletion. If you look into the groundwater system right over here in Baton Rouge, it's a very complex aquifer system. We can down to around 900 meters, 3,000 feet below land surface. And we have hundreds of pumping wells tapped in different aquifers over here at the different depths. You can see starting you can see this USGS groundwater level data over last 50, 60 years. So we have more than 300 feet groundwater level drops. And to understand this groundwater simulation, we will be able to look into a very, very detailed aquifer system over here. And that gives us a tool for soil water intrusion and for land subsidence studies. Also in the Chico aquifer, we look into a cone of depression in the two areas, which is confirmed by the previous publications looking into the Chico aquifer simulation, and we have a constant groundwater level decline in the lower Chico aquifers, and we have a very low groundwater levels in the 500% and 700% because of industrial pumping in the Lake Charles areas. The spot aquifers also confirmed by the previous USGS modeling that we have a spot aquifer in the north central areas. We do have big cone of depressions right over here in the Monroe and Western Monroe areas. presents right over here. New Orleans is also a very important because we saw groundwater flooding in the New Orleans low-lying areas. 50% of land in New Orleans is below sea level. That's why the groundwater seepage we can calculate is extremely important to New Orleans area to understand the high groundwater seepage is actually very close to the Lake Pontchartrain areas, based on our groundwater model. Because of the natural levee around the Mississippi River, so basically you don't see any seepages around the Mississippi River because of high ground. We also have a groundwater model we can to understand the coastal restoration, looking into the Mississippi River Delta surface water, groundwater interactions. This is the Mississippi River toward to the Gulf of Mexico, which is in this area, and we will look into how the groundwater river stage, Mississippi River and groundwater interaction at a different sense. So we can look into the details. So instead of several pieces of groundwater model, we do have now an entire Louisiana groundwater model for different different study at different areas. So next slide, I'm going to talk about we advanced our groundwater model toward to the borehole and the airborne geophysical data integration. I'll make this really quick. Airborne electromagnetic survey has become very popular in the United States. It's a game changer because through these surveys, you can really understand what's going on underneath, okay, in a very economic, cheap way. Especially USGS invest a lot of effort to do the AEM surveys in the lower Mississippi Gulf regions over here. So we use USGS data combined with our well logs data. We will be able to, through a framework over here, to create a lithological model. So by integrate the well log data and the AM data through the process and the geostatistics, we'll be able to really delineate the probability of sand within the Mississippi River alluvial aquifer. And we can see a very detailed percentage of aquifers. Over here, on the top, you have a clay cap, and then you have a very thick, more than maybe 50 meters thickness in alluvial aquifers. I can look into different cross sections. So AM really help us to understand the MRVA very well, and we can know the MRVA at different depths, different thickness, and understand where are the aquifers and where are the aquitop. So it's really handy over here. And then once we have a lithological model, then we revisit resistivity data, and we really look into the low resistivity within the aquifer. Then we can build by combining the borehole data, AM resistivity data, and look into the resistivity data in the sand, we'll be able to basically understand the chloride concentration within the aquifer. And we build a machine learning model to build through some TDS data, locations, aquifer resistivity, and through deep learning, we will be able to estimate chloride concentration within the Mississippi River alluvial aquifer. So that's another advantage of using airborne data. So this figure just shows you that we have resistivity data from the USGS, go through the machine learning models, we will be able to translate into the chloride concentration, and finally we can understand, especially in the bottom of MRVA, we will know the resistivity, the chloride concentration distributions at the different locations. And those showing the cross sections about those chloride concentration over here. And we published the paper in the Science of Total Environmental to really tell the readers that why we have solar water in the Mississippi River alluvial aquifer. And because of time constraints, I will suggest you look into these papers and understand where's the source of the salt in this area and what is the process such that those salts can come into the Mississippi alluvial aquifer. We also have AEM data in the coastal Louisiana that we can use. We have Cheniere Plain, we have a Mississippi alluvial deltaic plain, and we have Chafalaya Basin. We want to look into the groundwater, soil water intrusion in these areas, in the coastal lines. Again, we have a procedure to combine resistivity data and the physiological model together through a relation that we will be able to build a chloride estimation to map the soil water plumes based on different data. So we collect the chloride data from USGS, from the Mississippi River, and from the clean stations. And this is the results that we can look into a detailed resistivity, AEM resistivity distributions within the Chico Aquifer and within the MRVA. So you can see on the top, we have a high resistivity represents the sand. And close to the coastal lines, then you have a blue areas, which represent the low resistivity, which probably represents the soil water intrusion and salinity in the coastal areas. And we build a regression models, AEM resistivity and versus chloride concentration. Given this regression model, we will be able to translate the resistivity into the chloride concentration for the coastal Louisiana. So that's the results we have. And we look into the soil water distribution in the Chico Aquifer. You can see the red color will be high chloride concentration above 3,000 parts per million. You see the blue areas, which is basically the fresh water. And you can see the soil chloride, you have an upcooling of soil water from the base of the Chico Aquifer because of agricultural pumping to drag soil water upward. And we also compare to the past USGS publications. It's very interesting to see the soil water intrusion in the southwest Louisiana, in the coastal area here, and there's a ton of soil water over here, which actually reflect in the AEM data we have. We have soil water here, and also they have a ton of soil water intrusion. So it's very amazing that the AEM data really can pick up those low resistivity signals, which reflect to the past USGS studies. And I will skip this one because the 14 also impacted the chloride distributions, which help us to understand the fault barrier or the conduit in the southern Louisiana. All right, so this is the soil water distribution in the Merva, which you can see a ton of chloride within the Chafalaya basins, which that's why start to understand why when USGS draw these freshwater aquifers, why this has been left blank over here. It's because of really of soil water, maybe through the paleo estuary in the past.
Just a quick note, Dr. Tsai, that we're running low on time.
Okay, finish this one. Okay, so I'm basically done. I'll keep this one. So working toward to the Gulf model. So what we are doing is to build a much bigger groundwater model for the lower Mississippi Gulf, which is my students are working on this one. And this is the current progress that we already have a geological model, and we are going to start to split the model into for groundwater systems. And in the future, hopefully, we'll be able to analyze the Texas data. And so we know the Texas data, we'll be able to build the groundwater model for Texas coastal areas. All right, so that's the concluding remarks. MODFLOW 6 is a game changer. It really enables us to build a high-resolution groundwater model, especially for the Gulf groundwater model. Airborne geophysical survey is also a game changer. It's really enables us to see and confirm the saltwater intrusion in aquifers and also in the Mississippi River. So in the future, we are going to integrate the MODFLOW 6 borehole data and the AEM data to develop a saltwater intrusion model and the land subsidence models. That's the future, what we are going to do in the next maybe 3 to 4 years. All right, thank you very much.
All right, thank you very much, Dr. Tsai. That was very fascinating, at least to me personally. I really enjoyed that. We've got a few minutes for questions here. You're welcome to drop your questions in the chat. I will read them, and then if needs be, people can pop open their mics. First question here, did you have a chance to monitor chloride concentration over time and use it for history matching as an indication of natural recharge from a lake or the sea? And did you correlate groundwater level changes with the subsidence rate?
Okay, it's a very good question about the chloride changes in time series. Okay, AEM data only give you a snapshot of what's going on at the time of surveying. So my answer is the answer is no, we don't have a time series AEM surveys. We only have a snapshot. So we use that and correlate to the past chloride data. So we, under the assumption that maybe at the last decades, the chloride will not change too much, that you can try to understand the big picture of a saltwater intrusion in large scale areas. That's give us not a real detail, but big picture. The second is the subsidence. MODFLOW 6 can do subsidence simulation, and it can do very well. I did not show in this area in this talk. Actually, we have a subsidence model in the Baton Rouge area using MODFLOW 6, and we got a very good fit in the compaction data fit to the extension meters in the Baton Rouge area. So yes, MODFLOW 6 has the capability to do compaction simulation relating to the groundwater level changes.
Right, fantastic. Another question here caught my attention mentioning submarine groundwater discharge. How can I find out more about this? Can you map freshwater discharge with electromag survey?
Yes, you do. Okay. We present this one actually in the one of my PhD dissertation, and we have a faculty from the oceanography. So immediately recognize that because we can, well, I did not talk much about this one. We can map a soil water in the Mississippi River. We can see the soil water intrusion in the Mississippi River mouth, which means that we'll be able to see the soil water chloride concentration in the estuaries, okay, in the coastal lines.
Hmm.
Yes, the
Yeah.
AEM has the, sorry, AEM has that capability, and actually USGS is doing that in 2025. Actually, USGS are doing new AEM surveys along the Gulf of Mexico.
That's interesting. Then sort of a related question here on AEM. What exploration depths were achieved with the USGS surveys?
Okay, it depends on the device of the AEM machine, but in general, the signal can penetrate down to the 400 meters below land surface. So you can imagine that you can get the AEM resistivity data up to 400 meters, but there's a depth of investigation which give you much less uncertainty, okay, which is around 240 meters. And this 240 meters is deep enough to understand the Mississippi River alluvial aquifer and the Chico aquifer.
Okay, yeah, that makes sense. Got a couple more good questions here. Going back to your sort of modeling techniques, what software did you use to create the Helm and the dipping and non-dipping models?
Okay, we create our own. I'm a kind of old guy. Okay, so we basically we we wrote Fortran code, not Python, Fortran. We wrote Fortran code. We know how to do the dipping, translate from the dipping to non-dipping and back to the dipping, and also create the DISU files and create the exchange files. It's all done by Fortran.
That's a
We have
vanishingly rare skill, Fortran coding right there. Another question here, could kind of again going back to your modeling processes, could you please discuss your time savings from splitting the models and creating exchange files versus running a single model, as well as complexities created during calibration for splitting?
okay. I think that's a good question. That I know we don't have much time over here. I give you the ideas about splitting. Okay. Once we create a geological model like this, we have a very efficient code to create DISU packages and exchange packages very fast within few minutes. Okay, so we have a very efficient, but in terms of model calibration, okay, that's a different story. Model calibration depends on the model runtime, right? So we did a test. Okay, I did not show here. We did a test that we have 23 models. If we run a single core for the very simple settings, one core, it takes 60 minutes to finish. However, if we have 23 models, we run 23 cores, the runtime decreased to 5 minutes.
Oh, wow.
I decrease. That's the power of MODFLOW 6. This is parallel version. You can reduce 12 times. So if you split more, maybe you can get a less computation time. Yeah.
That's amazing. It always helps to reduce computation time. Well, we've got
Yeah.
about 2 minutes left here. I don't see any more questions in the chat at the moment, so I'll ask one of my own, right? My prerogative of being a moderator. So can you just give us, I'm just curious, can you give us some examples of how these new models may be being used by the state of Louisiana or government entities of the state of Louisiana for groundwater management and planning?
Okay. That's non-technical questions now. So okay.
That's right.
We build this groundwater model, especially very important for the capital area, right in the Baton Rouge area over here, because we have a solar water intrusion, we have land subsidence issues, we have groundwater depletion issues here. So it's mainly for here. And we are hoping that people can see the power of our statewide groundwater model and gradually can elevate to connect it with surface water model, because we have this Louisiana watershed initiative, which is the build lots of surface water models, hydrological models. Hopefully we can combine together in the future and we can understand the surface water groundwater interaction to solve several flooding issues in Louisiana.
Interesting. Well, we've got about 1 minute left. We got one last question that came in. If you can answer it quickly, that'd be fantastic. Oh no, wait, where did it go? I thought there was, but I think it was retracted. So, okay, no problem. Well, thank
Okay.
you so much for your time, Dr. Tsai. This was a fantastic talk. Appreciate everyone joining us.